So Big Idea 5 focuses on thermodynamics, the effect that energy has on changes in matter, how we can quantify it, how we can use these changes in energy to predict whether or not reactions will be spontaneous, by how many kilojoules and joules it will require to make them spontaneous, how much heat will be released, etc., etc. So before we get into that breakdown, I just wanted to clarify a difference between two common terms, energy and temperature. We usually think of these things as being the same concept, but energy and temperature are vastly different. In fact, temperature is just a measure of energy, a particular type of energy. It's a measure of the average kinetic energy of a substance. So we could say that they are directly related. If you increase the kinetic energy, you're going to increase the temperature of a substance. And the way we've seen these before, this should be reviewed by now, is through Boltzmann distributions, where we have kinetic energy on our x-axis and number of particles on our y-particles. And we get distribution curves that look something like this, or like this, where the peak represents the average kinetic energy of the molecules at two individual temperatures, where T2 is out here, T1 is here, and we know that T2 is greater than T1. So just to clarify, whenever we're referring to temperature, we're talking about a measure of the average kinetic energy of a substance. How much kinetic energy due to motion, does each molecule have in that substance, and then the average of it. We also know that temperature always can be used to quantify and determine heat flow. We know that heat always flows from hot to cold, always. And we usually determine that based on this temperature, from a higher temperature substance to a lower temperature substance. We call that a spontaneous reaction. Using thermodynamics, we can actually quantify and predict by measuring the amount of energy released in these type of spontaneous processes, for example. So, for example, the first thing we learned about thermodynamics was the laws of thermodynamics, okay? And there are the two main ones that we need to be able to walk away with. The first law of thermodynamics is that energy is constant. It cannot be created or destroyed in a reaction. Rather, it just changes form. It can go from chemical energy to electrical energy, from potential energy to electrical energy, okay, mechanical to chemical. Energy can change a variety of forms, but it will always be constant. The amount of energy in a system is constant. The second law of thermodynamics refers to entropy, and the idea that entropy of the universe is always increasing. It's always greater than zero for a spontaneous process. So the power in this idea, this second law of thermodynamics, is that therefore reactions can only be spontaneous in one direction. So if we have a reaction from A to B, and we know that delta S of this reaction is equal to 50 joules, okay, per mole Kelvin, we know that's a positive value, so the entropy is increasing as we go from A to B. So we would say this is spontaneous. If we reverse the reaction, and we went from B to A, now the entropy value gets reversed. It's now negative, and that's a non-spontaneous reaction. So since the entropy of the universe is always greater than zero for spontaneous reactions, we can say that spontaneous reactions only occur in one direction. Or another way of saying that is a reaction cannot be spontaneous in two different directions. So how can we determine the spontaneity without just using entropy? Well, we know about we know three different values and how to use them with their standard states. So those three values were enthalpy, delta H, entropy, delta S, and Gibbs free energy, delta G. Now this is not written in its standard state. The standard state enthalpy would be written as delta H naught, delta S naught, and delta G naught. Okay? This might seem like a very small difference, but this little symbol here signifies something very important. It signifies that all the molecules and atoms and elements that we're interacting with are in the standard state. So what does that mean? Well, it means that if we're talking about pressure of a gas, it's at 1 atmosphere. If we're talking about concentration of a solution, it's 1 molar. If we're talking about temperature, it's 298 Kelvin, which is the same thing as 25 degrees Celsius. And if we're talking about the enthalpy of formation is equal to 0 for elements in their standard state. So for example, solids, diatomic molecules. Just like determining their oxidation numbers, their standard enthalpy of formation is 0. So how can we apply that? Well, let's look at this reaction up here. We have 2 moles of methanol combining with 3 moles of oxygen to produce 2 moles of carbon dioxide and 4 moles of water vapor, H2O gas. So a quick little check for understanding. What type of reaction is this? You should have said that it is a combustion reaction because we have a molecule combining with oxygen to produce carbon dioxide and water. Now we want to figure out what is the enthalpy of formation of this reaction. Well, the way we do these problems is we're usually given a table like this, where the enthalpy of formations of each compound is given. So if we want to figure out the enthalpy of the reaction, delta H naught of the reaction, we know that it's going to be equal to the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. So, if we're given this table in this equation, let's go ahead and solve that. Well, delta H naught of the reaction is going to be equal to the sum of delta H naught of the products. Well, what are our products? We have CO2 and H2O with coefficients of 2 and 4. So, look in the table, enthalpy for CO2, negative 394, but there's 2 moles of it, so times negative 394, plus 4 times the enthalpy formation of water, negative 242. Subtract the enthalpy of formation of the reactants. Well, CH3OH, it's negative 201, and I have 2 moles of it, 2 times negative 201, plus enthalpy of formation of oxygen. Well, it's not given in the table. Am I stumped? No. O2 is diatomic, it's in its standard state, so it has an enthalpy of formation of 0. Boom, so that would be the setup. If we do the math, we come out to a final answer of negative 1,354 kilojoules. Boom, so that would be the setup for these problems. We could also solve for one of these values if we're given the delta H naught of the reaction. There's a lot of ways we can manipulate these ideas. We also need to know about bond energy. The definition of bond energy is pretty simple. It's the energy needed to break a bond. And we can measure this in kilojoules and joules. And if we want to use bond energy and apply it to a problem, well, first thing we need to know, since we're breaking a bond energies are always going to be greater than 0 because they're always breaking bonds is endothermic. But if we're trying to figure out if an overall reaction is endo or exothermic, we have to figure out the bond energy for all of the molecules involved. And it's the same kind of equation as before. Delta H naught is equal to the sum of the bonds broken minus the sum of the bonds formed. Okay, this is how we use the relationship for bond energy. I'm not anticipating very many problems or mentions of bond energy on the AP exam, but something to be aware of. We should be more familiar with enthalpy of formation. We can also use enthalpy of formations when we're doing problems like involving Hess's law. So remember, Hess's law was the idea that the overall enthalpy of a reaction is equal to the sum of the enthalpies of all the steps in that reaction. So this was that problem that I did on the board that I totally messed up and we got completely lost and I said scrap it, forget about it, that nasty day. Well, I chose a simpler example this time, so life should be a little bit better. If we have this overall reaction here, 2 moles of A react with 1 mole of B to produce 1 mole of C, and we have these 2 steps below, we want to figure out what is delta H naught of the overall reaction. Okay? Well, we got to figure out how are these steps going to go together. Well, A plus B is going to make X, and then C is going to produce X plus A. If I combine these reactions as is, I'm going to be left with, hopefully you can see this, C, A, and B as reactants and 2X and A as products. That's not going to add together to give me this. So I'm going to have to manipulate one of these steps. And hopefully you can see it. We're going to need to take step 2 and reverse it, flip it. So now we'll be left with A plus B produces X, and X plus A produces C. Well, since we flipped the reaction, we now also have to flip the enthalpy value. So step 1 we didn't do anything to, it's still 100 kilojoules per mole. Since we reversed step 2, it's now going to be a negative and negative 50, so a positive 50 kilojoules per mole. So now if I want to figure out delta H of the reaction, let's check to make sure that these add together. Well, X is canceled because one is a reactant, one's a product, so I'm left with 2A's plus B produces C. Oh, yep, that's exactly what I wanted. So now I got to add the enthalpies as is. 100 plus 50, that gives me 150 kilojoules per mole. So I could figure it out, the enthalpy of the reaction for the overall, if I'm given the enthalpies for each step. It's kind of like a puzzle, got to fit them together so they add up to make the overall reaction. We also need to know how to deal with phase changes. So we saw this in an earlier video already, the definitions of condensation, evaporation, freezing, and melting. But we need to know how to interpret and analyze phase diagrams. So that's what we have over here. This is a phase diagram. So the way these usually look is we have solid, a liquid, and a gas. And what this shows us is we always have pressure on the y-axis, and we always have, this looks like a lowercase t for time. This should actually be a capital T for temperature. So let's say that, we're at a temperature right here of 200 Kelvin and a pressure of 1 atm for some compound. Let's say we increase the pressure until we get to 4 atmospheres, but we keep it at constant temperature, whatever this substance is. Well, it's going to move from the gaseous phase and then cross this line and move into the solid phase. So the type of question you might be asked is, at what pressure and temperature would evaporation occur? At what temperature and pressure would condensation occur? And that would involve using a diagram like this. One property that compounds have, based on the amount of molecules in the gaseous phase, is the vapor pressure. So this is the pressure exerted by gas molecules above a liquid. So if you have a sealed bottle here with a solution inside, okay, some of these molecules are going to evaporate, okay, turn into a gas, boom, and some are going to be condensing at the same time. Okay. The idea is, since some of these molecules are in the gaseous phase, they'll be exerting a pressure on the surface. That pressure that they exert is the vapor pressure. And to connect it back to intermolecular forces, if a substance has more IMFs, that means the molecules will stick together more likely. They're stronger, more strongly attracted to one another. So molecules are going to be more likely to be in a liquid phase. They don't want to break apart. So that means we have fewer gas molecules, and if we have fewer gas molecules, we have a lower vapor pressure. On the other hand, if a substance has low IMFs, intermolecular forces, that means these liquid molecules are not attracted to each other very strongly, so more of them are going to evaporate into the gas phase, and therefore we're going to have an increase in vapor pressure. So this is just spiraling in our idea of intermolecular forces to talk about phase changes. We also did labs and discussed how to actually determine enthalpies of formation using a process called calorimetry. Okay? Basically, through calorimetry, we are able to isolate a system to determine how much heat it either gains or loses in a reaction. And then if we know the number of moles that were involved in that reaction, we can determine the enthalpy of that reaction. So the main equation that we learned for calorimetry, this should sound familiar, is Q equals mc delta T. Okay? Where Q is heat in joules or kilojoules. M is mass in grams or kilograms. T is our change in temp, final minus initial in Celsius or Kelvin. And last but not least, C is our specific heat. Okay. What is the specific heat? Specific heat is a measure of how much the temperature of a substance changes when it absorbs heat. So if a substance has a high specific heat, that means it changes temperature a lot when it absorbs heat. So examples of compounds that have high specific heats, that means they change temperature very easily. Okay, that would be like a metal. Metals have high specific heats. They change temperatures very easily. Compounds with low specific heats, you can add a lot of heat to them, a lot of joules, but their temperature doesn't change very quickly. So we've done a lot of practice problems where you're given 3 out of these 4 variables. You got to solve for the fourth. Those are more basic. We're just going to practice a more complicated one together. So this problem says calculate delta H. I couldn't type that in on the iPad. If 25 milliliters of 1.5 molar HCl and 30.0 milliliters of 2 molar NaOH are mixed and the temp of the solution rises from 23 Celsius to 31.6 degrees Celsius. Assume the density of the solution is 1 gram per milliliter and the specific heat is 4.18 joules per gram degree Celsius. Whoa, there's a lot of information. Okay. Well, we're trying to find delta H. Okay. Well, if we remember, the delta H of formation is going to be equal to Q over the number of moles. Okay. So in order to figure out delta H, we need to know 2 things. We need to know the amount of heat, Q, involved in this reaction, and we need to know the number of moles of product made in this reaction. Okay. Well, let's figure out Q first. Well, we know Q is equal to mc delta T, and just to be clear, there's no difference between this capital Q and this lowercase q. Same thing. Okay. Well, the mass, well, I'm not given any masses, but I am given the volumes, 25 milliliters and 30 milliliters. So if I'm talking about the total solution, I got to combine those. That gives me 55 milliliters. And if I know that the density is 1 gram per milliliter, that means every milliliter has a mass of 1 gram. So therefore if I have 55 milliliters, I have 55 grams. The specific heat is given to me, 4.18 joules per gram degree Celsius. And the change in temperature is the final minus the initial. Well, 31.6 minus 23.0 gives me 8.6 degrees Celsius. So if I set that up, I do all the multiplication. Let's check my units. Well, my grams cancel, my degrees Celsius cancel. So I'm left with joules. And if I do the math, Q is equal to 1,970 joules. So 1,970 joules were transferred in this reaction, released from the solution to the thermometer. So I have Q. This part's done. Now I got to figure out the number of moles. Okay. Well, let's go ahead and do that on the next page. I know that I'm reacting HCl and NaOH. So if I wrote the equation for that, HCl plus NaOH, I know this is an acid-base reaction. I'm just going to make a salt, NaCl, and water, H2O. Okay. I need to figure out if this reaction is occurring. What is the limiting reactant? Well, we've got to figure out the moles of each. So 25 milliliters, 1.5 molar, 30 milliliters, and 2 molar. So you could figure out the moles of each, or you could just kind of look at this quickly and recognize HCl has a lower concentration, so that means there's fewer moles per liter, and I also have a lower volume. So therefore I must have fewer moles of HCl. So it's my limiting reactant. So all I care about is how many moles of HCl were involved in the reaction. Because remember, the equation we're trying to solve for is delta H equals Q over moles. So I have 25.0 milliliters. Well, I know you guys got to have this memorized. 1 liter is 1,000 milliliters. Or if you just want to remember, move the decimal to the left 3 times, converting to liters. And I know, based on the molarity, there's 1.5 moles for every 1 liter. So my milliliters cancel, my liters cancel. If I do the math here, I'm left with 0.038 moles of HCl. And since the ratio here, if we look at the coefficients, is a 1:1, because remember this would be the net ionic equation for any acid base, these are all spectator ions, would be H plus OH makes H2O. Therefore I must also have 0.038 moles of H2O produced. So let's plug the values in. I know that delta H is equal to Q over moles. I remember my heat from the page before was 1,970 joules divided by the number of moles, 0.038. And if I do the conversion, I'm left with 52,000 joules per mole, which we could also convert to 52 kilojoules per mole. So that would be delta H naught for this reaction. Boom. Those are the big concepts from Big Idea 5, Thermodynamics and Changes in Matter. We'll work on practice problems in class and wrap up with Big Idea 6 tomorrow.